Wow, you guys certainly are ambitious to keep coming back for more of my video blah blah blah. But I know it's all in the name of learning chemistry. Yeah. Well, this little video is I want to cover some discussion questions that I don't think I'm going to get to this year. As you can see, I made this little discussion document last year, but we're doing something different this year. So the topic is mechanisms and elementary steps. Imagining molecules colliding or decomposing or in one chemical event changing in some way. There might be a series of events that add up to an overall reaction, but in any case, and this is kind of a big if this CH3NC compound changes or isomerizes from being bonded from the nitrogen to the carbon to the carbon to the carbon, we say it's a first order event if there's only one of those molecules. And same story here on the O3. If there's only one O3 molecule in an elementary step, then I have it one of those molecules to the first power. On the other hand, if two molecules are colliding with an O3 and an NO here in this second of the four reactions, then I'll have one O3 and one NO, one O3 and one NO to the first power. That's 1 and 1. Now this is breaking a big rule that we actually warned you against earlier in the chapter, which is not to do this. But, big but, and big if these are elementary steps, then not only are we allowed to do this, we're instructed to do this. It's the way we hypothesize about the dependence of the rate on that elementary step. So with a 1O3 and 1 oxygen atom, 1O3, 1 oxygen atom, I have one of those and one of those, and so the rate according to this elementary step, or dictated by that elementary step, would be 1O3 and 1 oxygen atom. I know, this seems kind of really weird until you get the hang of it. Here's a clicker that we're not clickerizing, but we'll just go over the example. So I have a proposed mechanism, and I'm supposed to find out maybe what a slow step is, or thinking back to exercise 35 in quotes, which we may never have done, but we found the natural logarithm to linearize the concentration versus time data. I don't even know what the overall reaction is yet. I could add these up and find out. I think I'll do that. In any case, if the natural logarithm linearizes the data, I know it's first order in the reactant. Oh, I should really add these up and see what cancels. H2O2 as a reactant, another H2O2, OH. Oh, here I have two OHs. That's going to cancel with these two OHs. And I have an HO2 is going to cancel with the HO2 over here. Two waters over here and an oxygen. I think that's going to be my overall equation. I'm going to write that down in a second. But in any case, if I have one reactant, H2O2, and the natural logarithm linearizes the concentration versus time data, think back a little ways, you're pretty sure it's first order in H2O2. I really should have. I didn't do it. I really should I should write out and cancel this OH and this OH with those two OHs, cancel this HO2 with this HO2, and then I would have left over two H2O2s react to give two H2Os and one oxygen gas molecule. Alright, I'm not so sure what's going on. I know what's going on. So the point of this whole story is if there's more than one elementary step in a mechanism, like perhaps this molecule decomposes into these two, then this C4H9 plus runs into a water and creates this, then that reacts with another water to create this. Then, like in a Hess's law type way, I'll add these together and see what cancels. This is an intermediate, cha-ching, cha-ching, that cancels. I have two waters here that are going to be left over, and this molecule is a reactant as well, but I think this one will cancel with this one. The slow step, the slow mechanism, whichever one is slow, sometimes we're told which one is slow, or which one we think is slow, the slow step always determines the overall rate law. Oh, there I canceled them. So if I have a slow step, or if I'm told a slow step, or if I can figure out a slow step, that reactant or reactants in the slow step, in the slow elementary step, determine the overall rate. So the rate must be this, some constant times C4H9Br to the first power. Oh yeah, I had those intermediates which I canceled, and I wrote down my final equation there, which is sometimes handy to know. Alright, what are we supposed to do here? Oh, I see, right away they tell me a slow step. So what do we know that's special about the slow step? Oh yeah, it determines the overall rate. So if I have 2 molecules of NO2 in the slow step, I'm going to predict, excuse me, that this overall rate of this overall reaction will be second order in NO, because I have 2 of those particles colliding. And if that's the slow step of an elementary step in the mechanism, if the rate constant for this reaction is a value of a gas phase, from those units I probably could figure out it was second order as well. At a particular temperature, what would be the initial rate after starting with a pressure of this much NO2? Alright, so on both of those accounts I can say it's second order on the account that this is the slow step and I have 2 of those NO2 molecules in the mechanism, slow step of the mechanism. I can write second order, or I could look at this constant, try to figure out if the units of the constant are in 1 over torr seconds, and I want my overall rate to be in torr per second, then I'm pretty sure it would be, yeah, second order. In any case, don't forget to square the pressure of the NO2. That's what the rate law says. If I'm using pressures instead of concentrations, take that number squared, square that number, multiply by the constant. That should predict your overall rate for the reaction. Let's see. The activation energy for the reaction is 125 kilojoules per mole, and the delta E is negative 216. What's the activation energy for the reverse reaction? I have no idea. I need a picture. Picture says 1,000 words, so let's look at it. Oh yeah. So if I start here and end here, the delta E is negative 216, or delta G, change in free energy, and the EA activation energy. But if I was going from here to here, if I just add that, so if I add 1 mole of this and 1 mole of this, it would take 125 kilojoules to get up over that barrier. But if I'm going in reverse, I start down here at the NO and CO2, then I have to pump the energy in continuously, and that would be 125 plus 216 for a total of 341 is the difference between here and here to get down to there. That's weird and interesting. Alright, next question. Activation energy for the reaction, and the delta E. Oh yeah. So I wonder if you feel like pausing the video, how nerdy would that be to pause the video and try this yourself? What's the activation energy for the decomposition? Decomposing HI. Oh, that's backwards, isn't it? So if I have the delta E and the activation energy for the forward, how do you find the activation energy for the backwards? Here comes the answer. Oh yeah. So if I have, so it's endothermic at 28 kilojoules, and the activation energy is 167. So if I want to go from here up to here, so the reverse looks like it has an activation energy of 167 minus 28 to get from here over this hill to here. Interesting. Oh my, there's a whole lot of data here. We're making a graph. Here I have some data of the rate constant K versus the Kelvin temperature. They tell me a plot of the natural log of K versus the reciprocal of the Kelvin temperature has a slope of negative, 11,000-ish Kelvin, and the y-intercept. Find the activation energy What's the value of the frequency factor? I'm not so concerned about that, but I could probably find it. Calculate the value of K at 25 degrees Celsius. This is an important mathematical relationship and graphing technique you should think about. Memorize it. The natural logarithm of the rate constant as a concentration as a function of the reciprocal of the Kelvin temperature, it ends up being a straight line. And that straight line has a negative slope, and that slope is equal to the negative of the activation energy divided by the gas constant. So, previous to this, we had no idea how to calculate the activation energy, but if I measure the rate constant as the temperature gets warmer and warmer, or colder and colder, and I just linearize the data like this, I can indeed theoretically find the value of the activation energy. 8.31 joule per mole Kelvin times 11,000, that's the slope, negative of a negative. It comes out to a big number, 91,400 joules per mole, or usually it's expressed in kilojoules. The mathematical relationship looks like this, the Irradiance equation. The natural log of A is the intercept. Yeah, natural log of A is the intercept, so the frequency factor A, describing how quickly they collide and such. But I don't think we'll go there on the test at all. But this, we might actually ask you to practice that quite a bit, this purple thing here. Oh yeah, and the constant, little k, in this, the rate constant at 25 Celsius, 298 Kelvin, there's my activation energy, e to the negative, yada yada, and the frequency factor then after I've found that goes there. That's going a little bit too far, but good to think about. Fun with math. Is that an oxymoron? Can you have fun with math? I can. For the first order reaction, the rate constant, and oh, I see. So here they're telling me two rate constants for two different temperatures. This is the 2-point form of the Irradiance equation. You should become comfortable with using this, although it's a little bit tricky with the temperature 1 and constant 1 and temperature 2 and constant 2 and the gas constant and energy units and the activation energy. But in any case, you should practice it a little bit to make sure you can get it right on your calculator, which is actually a challenge. So I have a temperature of 273 and the rate constant was 0.046, and I have a warmer Kelvin temperature of 293 and the rate constant gets larger. Are you surprised that as the temperature increased, the rate constant went up and therefore the rate went faster, the reaction went faster? No, you're not surprised. In any case, the mathematics is divide that, take the natural logarithm. I take the reciprocal of this and then take the reciprocal of this and then subtract the two and get that small number. Then let's see, that would be flip-flop. Let me take this to the denominator over here and this to the numerator, and I find an activation energy. Again, that's usually in kilojoules. Interesting. Another one of those. Would the slope of a natural log of the constant versus reciprocal of the Kelvin temperature plot for a catalyzed reaction be more or less negative than the slope for the uncatalyzed reaction? Assume they're both first order. Well, here's what I thought. Yeah, they'd have different slope. So that since the uncatalyzed path goes slower and the catalyzed path goes faster, let's see. If it's first order, the slope of the line of the natural log versus time is the negative of the constant. So if I had a more negative, did I get this right? I hope I got that right. Let me think about that. Yeah, so the activation energy for a catalyzed reaction is less, and so the slope is not as great. Yeah, this is a steeper slope for the uncatalyzed and a greater activation energy. That's a tricky one. Think about it. And I think this is the last one I have. We have some, again, Kelvin temperature versus rate constant data. This is pretty poor, pretty poor regression, pretty poor data. I would like maybe 2 or 3 or 4 or 5 more data points to see if I can get a better correlation coefficient. because that dot, that point, and that point are kind of far off. But I took the reciprocal of the Kelvin temperature and the natural log of the rate constant, natural log of those, reciprocal of those, and I plotted them. I found a slope of negative 7337. Yeah, so from that slope, could I find the activation energy? Is that what I'm supposed to do? Looks like it. Oh yeah, from above. Then I click the last clicker. From that slope of that question above, find the activation energy. So it would just be what? The gas constant, the negative of the negative makes a positive activation energy, 61 kilojoules. Yeah, that's it. Is that it? That's got, no, there's another one. My word, this goes on forever. All right. So, oh, this is a good one right here. Catalyst versus intermediate. So if an O3 collides with an NO in this mechanism, it creates one NO2 and one O2. Then that NO2 collides with another oxygen atom. That's weird. To create NO gas and O2 gas. The NO2 here cancels with this one. That's why they're called intermediates. But if something occurs, if a species or an atom or whatever occurs before and after, it's present in the beginning and it's present in the end, but it cancels, it's called a catalyst. So, that's a tricky one. Before, in the beginning, and the end, a catalyst, but in between, intermediate, yeah, it's like here and here. I need some more examples of that. But in any case, this would be a tricky one. You can take the ratio using the Irradiance equation, the rate constant. Let's see, they're telling me the activation energy for the catalyzed and the uncatalyzed. Yeah, right. So activation energy for the catalyzed, activation energy for the non-catalyzed, and I have the gas constant in energy units and the Kelvin temperature, and the A terms cancel. The ratio of the rate constants comes out to 2.335. The rate constant for the catalyzed reaction is 2.3 times larger, which means the reaction goes faster. Interesting. Well, I didn't mean to go too quickly through that, but on the other hand, you can always rewind, ask me questions, look at a PDF. Thanks for watching, guys.